Modern airliners carry hundreds of passengers across continents every single day. They connect cities separated by oceans, mountains, and thousands of kilometers in just a matter of hours. Yet, despite the incredible advances in aviation over the last 50 years, one question continues to surprise many people. Why don't passenger airplanes simply fly faster? After all, when engineers want to build a faster car, they usually install a more powerful engine. Racing cars produce enormous horsepower, and the result is obvious: greater speed. It seems reasonable to assume the same principle should apply to aircraft. Why not build larger engines, push harder through the sky, and reduce every international flight by an hour or two? The answer lies in a remarkable fact that most travelers never notice. Whether you board a Boeing 737 for a short domestic trip, an Airbus A320 crossing Europe, a Boeing 777 flying across the Pacific, or the latest Airbus A350 carrying hundreds of passengers between continents, they all cruise at nearly the same speed. Most modern airliners spend the majority of their journey traveling between roughly 830 and 950 kilometers per hour, while maintaining an altitude of around 11,000 meters, or about 36,000 feet above sea level. That similarity is far from coincidence. These aircraft differ enormously in size, weight, passenger capacity, and engine power. A Boeing 777 has engines many times more powerful than those found on a Boeing 737. Yet both spend most of their flights moving through the sky at almost the same cruising speed. At first glance, that seems almost impossible. If one aircraft has much larger engines, shouldn't it simply fly much faster? The instinctive answer is yes. More thrust should mean more speed. But unlike driving on a highway, flying through the atmosphere introduces limits that are invisible yet extraordinarily powerful. Air is not an empty space that allows unlimited acceleration. It behaves like a fluid, pressing against every surface of the airplane. At ordinary speeds, engineers can overcome that resistance with better aerodynamics and stronger engines. However, as an aircraft accelerates closer and closer to the speed of sound, the atmosphere itself begins to behave differently. Smooth airflow starts to break down. Pressure changes become more violent. Tiny regions of air around the wings begin moving faster than the aircraft itself, creating effects that cannot simply be solved by adding more engine power. The faster the airplane tries to go, the more stubborn the sky becomes. What seems like a simple engineering challenge slowly transforms into a battle against the very physics of air. For decades, aerospace engineers have carefully balanced speed, efficiency, safety, operating costs, and fuel consumption, eventually arriving at a remarkably consistent cruising speed used by nearly every commercial jet in service today. It is not the fastest speed modern technology can achieve, but it is the speed where all of those competing factors work together in harmony. And that raises an even more fascinating question. If today's passenger aircraft already have incredibly powerful engines, what exactly prevents them from flying just a little bit faster? The answer begins with a mysterious boundary that pilots and engineers know all too well. The closer an aircraft gets to the speed of sound, the stranger the sky becomes. To understand why modern airliners rarely fly faster than about 950 kilometers per hour, we first need to forget the number shown on the speedometer, and instead learn a completely different way of measuring speed. Pilots and aerospace engineers rarely think in kilometers per hour or miles per hour when discussing high-speed flight. Instead, they use a measurement called the Mach number. Unlike a fixed speed, Mach is a ratio that compares an aircraft's speed to the speed of sound in the surrounding air. A Mach number of 1 means an aircraft is traveling exactly as fast as sound. Mach 0.80 means it is flying at 80% of the local speed of sound. This distinction is incredibly important because the speed of sound is not constant. It changes with temperature. Warm air allows sound to travel faster, while cold air slows it down. At sea level on a warm day, sound travels at roughly 1,235 kilometers per hour. But at the typical cruising altitude of around 11,000 meters, where temperatures often fall to about -56 degrees Celsius, the speed of sound drops dramatically to approximately 1,060 kilometers per hour. That means a commercial jet cruising at around 900 kilometers per hour is actually flying at roughly Mach 0.85, much closer to the speed of sound than most people realize. At first, nothing unusual seems to happen. The airplane remains stable, passengers enjoy a smooth flight, and the engines continue operating normally. But something remarkable is happening in the air flowing around the aircraft. Although the airplane itself may still be traveling below Mach 1, the air moving over different parts of the wings does not all travel at the same speed. Because of the wing's carefully designed shape, airflow accelerates as it passes over the curved upper surface. In some locations, that airflow can actually reach the speed of sound before the aircraft itself does. Tiny regions on the wing suddenly experience supersonic airflow, even while the airplane remains officially subsonic. This creates an invisible phenomenon known as local shock waves. These shock waves are incredibly thin layers where air pressure, density, and temperature change almost instantly. To passengers inside the cabin, nothing seems different, but outside the aircraft, the smooth flow of air begins breaking apart. The consequences appear almost immediately. Aerodynamic drag increases far more rapidly than engineers would expect. The aircraft begins to experience vibrations known as buffet, as turbulent air separates from parts of the wing. Flight controls become less responsive, forcing pilots and onboard computers to make constant corrections to maintain stability. Engines must work significantly harder simply to gain a small increase in speed, burning much more fuel while producing diminishing returns. This narrow range of speeds, where portions of the airflow become supersonic while the aircraft itself remains below the speed of sound, is known as the transonic region. It represents one of the most challenging environments in all of aviation because the airplane is caught between two completely different aerodynamic worlds. Engineers have spent decades designing swept wings, supercritical airfoils, and advanced flight control systems to delay these effects for as long as possible. But they cannot eliminate them entirely. Nature simply refuses to make the transition easy. As every modern airliner approaches this invisible wall, the atmosphere begins demanding an increasingly expensive price for every additional kilometer per hour. And that drag explosion is only the beginning. Once an airliner begins approaching the transonic region, engineers face a problem that is just as important as aerodynamics: economics. Building a passenger aircraft has never been about achieving the highest possible speed. It has always been about transporting hundreds of people safely, reliably, and profitably. That is why commercial aviation is governed not only by the laws of physics, but also by the laws of economics. At lower speeds, aerodynamic drag follows a relatively predictable rule. As an aircraft flies faster, drag increases roughly with the square of its speed. Double the speed, and the drag becomes about 4 times greater. Even under normal conditions, overcoming that additional resistance requires significantly more engine thrust and fuel. But as an aircraft approaches the speed of sound, this relationship becomes much more severe. The appearance of local shock waves and disturbed airflow causes drag to rise far faster than the simple mathematical model predicts. Engineers call this rapid increase wave drag, and it is one of the primary reasons commercial aircraft avoid flying much faster than Mach 0.85. At that point, Every small increase in speed demands a surprisingly large increase in engine power. Those engines, in turn, burn far more fuel to produce only a modest reduction in travel time. Imagine a flight from New York to London. Suppose engineers found a way to increase the cruise speed by about 10%. On paper, that sounds impressive. A journey that normally takes around 7 hours might be shortened by perhaps 40 or 50 minutes, depending on weather conditions and routing. Many passengers would probably welcome arriving earlier. But behind the scenes, the economics become far less attractive. Flying approximately 10% faster could require 20 to 30% more fuel, and in some situations even more, depending on aircraft type and atmospheric conditions. Modern jet fuel represents one of the largest operating expenses for every airline. For a single long-haul flight, that additional fuel may cost thousands of dollars. Multiply that by several flights every day, hundreds of aircraft, and an entire year of operations, and the result is not a minor expense, but hundreds of millions of dollars in additional fuel costs across a large airline's fleet. Suddenly, saving less than an hour no longer seems like a bargain. This is why airlines rarely compete by promising the fastest flights. Instead, they compete by lowering the cost of carrying each passenger. Every decision, from aircraft design and engine selection to cruising altitude and flight planning, revolves around one essential number: the operating cost per seat. The goal is not simply to move an airplane through the sky as quickly as possible. The goal is to transport every passenger using the least amount of fuel while maintaining safety, reliability, and comfort. A modern airliner flying at around Mach 0.80 or Mach 0.85 is already operating near the point where those competing priorities reach their best balance. Flying faster would reduce efficiency dramatically while offering only modest time savings that most travelers would barely notice. In other words, airlines are not selling speed. They are selling affordable transportation, and every kilometer per hour beyond today's cruising speeds comes with an increasingly expensive price tag. Yet this raises another fascinating question. If higher speeds consume too much fuel, why don't engineers simply redesign the airplane itself so it can fly faster, more efficiently? So, if fuel isn't worth it, why not redesign the airplane? At this point, it might seem that the solution is obvious. If the wings begin creating shock waves as an aircraft approaches the speed of sound, why not simply design better wings? In reality, that is exactly what aerospace engineers have been doing for decades. Modern passenger aircraft already incorporate some of the most sophisticated aerodynamic designs ever developed. One of the most recognizable features is the swept wing. Instead of extending straight out from the fuselage, the wings are angled backward. This seemingly simple design delays the formation of shock waves by reducing the component of airflow that strikes the wing directly, allowing the aircraft to cruise more efficiently at high subsonic speeds. Engineers later introduced another major innovation known as the supercritical wing. Unlike traditional airfoils, a supercritical wing has a flatter upper surface and a carefully shaped trailing edge that slows the development of local supersonic airflow while reducing wave drag. These wings allow modern airliners to cruise closer to the speed of sound without suffering the severe performance penalties experienced by older aircraft. At the tips of many wings, another familiar feature appears: winglets. Although many passengers assume they simply look futuristic, winglets serve an important purpose. They reduce the powerful wingtip vortices that waste energy and increase drag, improving fuel efficiency over long flights. Together, swept wings, supercritical airfoils, winglets, lightweight composite materials, and highly optimized flight control systems represent decades of continuous refinement. Every major manufacturer has invested billions of dollars to squeeze every possible percentage of efficiency from the atmosphere. Yet, despite all of these advances, none of them can completely eliminate the aerodynamic problems that emerge near the speed of sound. They can only delay them. Eventually, physics catches up. Crossing beyond roughly Mach 0.85 toward Mach 0.95 requires far more than simply refining an existing airliner. It demands an entirely different airplane. The wings must be redesigned to manage much stronger shock waves. The fuselage must become slimmer to reduce drag. The windows often need to be smaller because of greater structural loads. New materials are required to withstand increased temperatures generated by aerodynamic friction. Even the engines must be redesigned to operate efficiently under completely different airflow conditions. At that point, engineers are no longer improving a conventional passenger jet. They are creating an entirely new class of aircraft. History has already shown what happens when that challenge is accepted. In 1976, Concorde entered commercial service as the world's first successful supersonic passenger airliner. Cruising at approximately Mach 2, or more than twice the speed of sound, it could fly passengers across the Atlantic in less than half the time of conventional aircraft. From an engineering perspective, Concorde was an extraordinary achievement. However, its remarkable performance came at an enormous cost. Its engines consumed vast quantities of fuel. Operating expenses were exceptionally high. Ticket prices were affordable only to a small number of travelers, and its narrow cabin carried relatively few passengers compared with modern wide-body aircraft. Noise restrictions also prevented supersonic flight over most populated land, limiting the routes it could economically serve. Concorde proved that humanity could build an airliner capable of flying twice as fast as today's jets. What it failed to prove was that doing so made commercial sense. Eventually, economics proved stronger than engineering ambition, and the aircraft was retired. Its legacy remains a reminder that building a faster airplane is entirely possible, but building one that airlines can operate profitably is an entirely different challenge. So perhaps the question isn't whether we can fly faster, but after exploring the invisible wall of the transonic region, the soaring cost of fuel, and the engineering challenges hidden inside every modern wing, the answer to our original question becomes surprisingly simple. Passenger airplanes do not cruise at around 950 kilometers per hour because they cannot go faster. They cruise at that speed because it represents one of the most carefully optimized compromises ever achieved in engineering. Every commercial aircraft is designed to balance competing priorities that constantly push against one another. Fly more slowly, and passengers spend longer in the air. Aircraft complete fewer flights each day, and airlines lose valuable productivity. Fly more quickly, and fuel consumption rises sharply. Maintenance costs increase. Aerodynamic loads become more severe. Engine wear accelerates. Cabin noise grows louder. And safety margins begin shrinking as the aircraft approaches the complex physics surrounding the speed of sound. Somewhere between those two extremes lies a remarkably narrow operating window where all of these factors align. For modern commercial aviation, that window is typically between Mach 0.78 and Mach 0.85. It is no accident that aircraft built by different manufacturers in different countries, separated by decades of technological development, all converge on nearly the same cruising speed. They are all responding to the same physical laws. That is also why cruise speeds have changed surprisingly little over the past 50 years. While aircraft have become quieter, lighter, safer, and dramatically more fuel efficient, they have not become significantly faster. Instead of chasing higher speeds, manufacturers and airlines have focused on improvements that passengers rarely notice, but that transform the economics of flight. New engines extract more energy from every kilogram of fuel. Composite materials reduce structural weight without sacrificing strength. Sophisticated computer systems continuously optimize engine performance throughout every stage of the flight. Artificial intelligence and advanced software analyze weather patterns, jet streams, and air traffic to select more efficient routes. Even small improvements in wing shape, engine fan design, or flight management software can save thousands of liters of fuel across an aircraft's lifetime. Those savings may appear insignificant on a single flight, but across millions of flights every year, they become billions of dollars while reducing emissions and operating costs at the same time. The modern aviation industry has learned that making airplanes smarter is often far more valuable than making them faster. Engineers did not discover a way to defeat the laws of aerodynamics. They discovered the exact speed where physics becomes economical. That realization may be one of the greatest engineering achievements of the modern era, because it demonstrates that true innovation is not always about pushing beyond every limit. Sometimes it is about recognizing exactly where the limit should be. The remarkable thing is that modern airliners aren't slow because engineers failed to make them faster. They're fast enough because, after decades of research, this is the speed where fuel, safety, engineering, and economics all agree. Every commercial jet flying quietly above the clouds today is traveling at nearly the same speed, not by coincidence, but because nature itself has drawn an invisible line across the sky. And for now, that line remains just below the speed of sound.